So as I was kind of ending up saying, static analysis tools, at least sound static analysis tools, remain something of a not necessarily researchy. Well, they have a researchy flavor. They're not ready to apply to our biggest codes yet. And so that kind of leads us to the dynamic analysis tools, and this is where we've had the really amazing progress in the last 7 years or whatever. These things have come along really well and really, I think, have made a difference. So what I'm going to focus on while I talk here is there's a lot of these tools. I'm going to focus on the LLVM-based ones, which you've no doubt run. So Address Sanitizers has made an enormous difference in undefined behavior, right? In undefined behavior checking. It's just this incredible thing. It's we had Valgrind before, but Valgrind ran too late on compiled code, and it wasn't very fast. Address Sanitizer is just enormously useful, and so it's not exactly what we want. I'm just going to have to be careful what I say because Scust is right there. So it's not exactly what we want. What we want is bounds checking, right? We want real bounds checking. Address Sanitizer is sort of a red zone-based approach, but it's so close to what we want, and it's there, and it's efficient that it just makes an incredible difference. And so I don't know how many of you, well, I guess I was already saying, but in the 90s, if you ran Purify on almost anything, it would just dump pages of crap. It was just incredible that anything ran. It's still a mystery to me why things used to run. And it's not the case anymore. Things, most software is fairly clean. So Undefined Behavior Sanitizer is another one that sort of, so Address Sanitizer, I'll just borrow some of the terms from Kostya's talk about this. It's sort of the hard checks, right? It requires quite a lot of infrastructure to work. Undefined Behavior Sanitizer are sort of the easy checks. These are the ones that don't require very much infrastructure to check. These are things like the shift errors that I talked about earlier in a Google Native client, signed integer overflow. Pointer overflow is one that recently was added, and so in C and C++, you can go, as you all know, you can go one element past the end of an array. You can compute that pointer, but you can't dereference it. But you can't go further, and you can't go before the beginning of an array, and you can't compare pointers between two arrays. And so pointer overflow checking is this kind of pretty efficient, pretty weak check, which only looks for pointers actually wrapping around the end of the address space, or the end of the pointer range. And this is in Undefined Behavior Sanitizer now, and it's pretty cool. It's a cheap check, and it does catch some things that sort of that people shouldn't be doing.
You can compare pointers between two different arrays, but it's unspecified behavior.
You can't compare pointers between two different arrays.
I mean, you can.
You can with something like standard, which is it? Standard less than?
Standard less.
But you can't.
Even though it is just unspecified behavior.
No, I don't. Yeah, so somebody find the quote. Yeah, we didn't need to argue. So like I say, a bunch of stuff has made it into Undefined Behavior Sanitizer. The alignment check stuff is actually really cool. This I don't know how many people run the full Undefined Behavior Sanitizer on big stuff, but the alignment checks dump a lot of stuff on typical software. And it's worth fixing those. Like I was saying at the beginning of the talk, not only because of architectures that don't do this, but because the compiler is actually free to assume that things are aligned and could break things in sort of weird ways. One of the things that is pretty cool is that UBSAN has capacity to check for also unsigned integer overflow. And this is pretty cool to watch people actually use this. People actually use this sometimes, and so of course unsigned integer overflow isn't undefined, right? It's perfectly well defined, but it's often indicative of a bug. It's not indicative of a bug in something like a hash table where you're trying to wrap the unsigned pointer around, the unsigned integer around, but it is indicative of a bug in many cases. And so turning this on selectively and whitelisting the cases where you want it to overflow actually turns out to catch quite a few bugs. And this is kind of an interesting thing is that, this sort of points to sort of an interesting issue, which is that we like to look at C and C++ and say that the undefined behavior, this aspect of the language sucks. So, this is something that at least, I've often said. And it's actually not really quite true because Java, for example, defines both unsigned and signed integer as wrapping in a two's complement fashion. And that robs us of quite a lot of error checking power. What it means is the language guarantees us semantics for something. People can count on it. It's not a bug anymore. And so the fact that C and C++ have all of these undefined behaviors actually, it opens the door to a lot of checkers. And finally, these checkers are sort of pervasively appearing. And this is actually, if you look at some of the very early rationale for C, they did design the memory allocation subsystem of C to support checking. That was intended all the way from the beginning, or near the beginning. And it's sort of unfortunate that it's only relatively recently that these checkers have gotten sort of quite good. So I'll just briefly mention some of these other ones. So memory sanitizer can check for use of uninitialized storage. Thread sanitizer can check for data races and deadlocks. And I don't know how many of you have used thread sanitizer, but it's really a pleasure to use. I mean, for a lot of kinds of bugs, at least that I make, I mean, I avoid writing threads when I can, but when I do write them and I have bugs, it really sort of mentions the problem fairly concisely. There's a new tool that's just under development, so you can't use it, and I really hope it comes to fruition. So it's a type sanitizer. So it's a type-based alias analysis sanitizer, and this is a big thing that's been missing for a long time. So the type-based alias analysis problems are lurking latent in an awful lot of codes. And they get sort of broken weirdly. And like I was mentioning earlier, quite a few codes disable type-based alias analysis just to not run afoul of these problems. A type-based alias analysis sanitizer, when this thing actually becomes available for LLVM, you should definitely run it on your big codes. This will be super cool. I expect it to really produce interesting results. And often what the fixes are going to involve is putting a lot of mem copies into your code. So instead of using type punning to do, instead of using cast to get different views or type unsafe views of memory, you basically end up copying them through char stars. That's kind of the hole that C and C++ have put in a type system for explicitly supporting these different views of memory. It's often the case that it's better to just mem copy a piece of storage into a region with a different type than it is to try to somehow use typecast to get two different views of the same memory. And so the bummer about this is that although those mem copies often get elided by the compiler, at least in sort of easy cases, when you turn on the optimizer, those mem copies aren't going to get taken out for debug builds. And so there's a risk that as we make our code correct with respect to type-based alias analysis, that our debug builds will get quite a bit slower. And this is something that web browser people in particular that I've talked to have worried about. So I don't know how that's going to play out, but I think it's going to be extremely fascinating to watch the type-based alias and to watch Tysan roll out, assuming it comes out in the next few months or year or whatever. It's going to be extremely interesting to watch what happens to people's code. So let's talk about there's some really interesting trade-offs between static analysis and dynamic analysis. And one of the awesome things about dynamic analysis is that it sort of finds bugs on popular code paths, right? It finds bugs along the code paths where you have test cases. And of course, this is both good and bad, right? It's obviously bad because you may have security bugs on unpopular code paths, but it's good because it actually lets you fix the problems that are at some level the most relevant first. So that's kind of a nice thing. Dynamic analysis tools don't give you typically false positives, so they're only giving you real bugs. And like I was alluding to earlier, I spent a lot of time looking at static analysis results. And the real problem there is you can spend a long time tracking down something till you get to the root cause, which is just an imprecision. It's just a false positive. And this is extremely frustrating. With dynamic analysis, if you're going to spend a few hours tracking something down, at least you know that you're going to get to something real, modulo a bug in the tool. And finally, the dynamic tools typically don't sort of inundate you with little minutia, things that are right, but that sort of are kind of technically wrong. Whereas a static analysis tool, this is almost their entire job in life, is to inundate you with sort of crap. Because that's what it really takes to make code correct. And it turns out that often we just don't want to pay the cost, right? Often we don't want to pay the cost of really making it correct in all the cases. It's just too hard for real code. So the drawback of dynamic analysis, of course, is that it's only as good as our test cases. And so this is why infrastructure like the stuff Kostya was talking about, stuff like OSS fuzz, is so incredibly important. Because the dynamic analysis tools are limited by test cases. If we can have really good testing, we get an enormous amount of leverage out of these tools. So there's an incredible synergy between the dynamic bug checking tools and the tools that exercise dynamic behaviors in our code, like the Clang fuzzer and like AFL and other tools like it. So there's a very strong positive feedback loop between these kind of tools, and this has really been beneficial for people like us. This has really made I think concretely made our lives better. Anyway, so fuzzers aren't a panacea, right? There's always, in complicated programs, especially ones that process really highly structured inputs, there's always corner cases that the fuzzer can't find. So Kostya's going to shake his head or something, but it's true, right? But they really do make a big difference in what we can reach. And so I made this kind of figure to sort of try to show the kind of universe of dynamic checking tools, or at least one view of it. So there's this kind of universe of undefined behaviors, and things like UBSAN and find one particular subset. Valgrind and address sanitizer find another subset. There are sort of pickier tools, pickier dynamic tools, like there's a couple of ones that are made by companies. One is made by a company, Trust and Soft, and there's another one by a company whose name I'm spacing right now. They make much pickier dynamic analysis tools, and those find most of the bugs found by UBSAN and ASAN, and also a bunch of others. And then there are quite a few undefined behaviors which aren't found by any of these tools. And the fact is, though, is that most of those ones that aren't found aren't the big ones that sort of matter. There's a lot of, I said earlier that there are 200 undefined behaviors. By the numbers, by far most of them aren't very interesting, and they could just be nailed by the standards committee. And I'm not, I don't go to these meetings, so I don't know why they haven't been. Anyway, so I just wanted to kind of put this up to sort of show you how I think of the kind of universe of undefined behaviors as they relate to dynamic checkers. So the last thing I want to talk about with respect to tools is mitigation. And so mitigation is pretty cool because dynamic checkers are great because they allow us to find things at debug time and fuzz time. And mitigation tools allow us to not be harmed by undefined behaviors that somebody else can trigger in deployed code. And so mitigation is really important because we have such a hard time with that last part of covering our software, with generating the test cases for that last bit of functionality. And so let me give some examples of mitigation. And one of the sort of unsatisfying things about mitigations is that there's not a lot of uniformity or portability. There's sort of this, it has a very patchwork kind of a feel. Well, let's talk about some of what people do. So Linux compiles, for example, with a flag which says, don't delete null pointer checks, even when the data flow analysis part of GCC can infer that that null pointer check can be deleted. And the reason is because the Linux has been burned for real a number of times by bugs like the one that I showed you, where something like a struct deref is done, or sorry, a pointer deref is done to a struct member or something, and then there's a null check. And the problem is by the time we got to the null check, the compiler has already inferred by the usage of the pointer that it wasn't null and deletes the null check. And this has caused real vulnerabilities, and they're sort of well-known examples of this causing problems. And the Linux kernel people are simply unconfident that they have eliminated all bugs of that class from their kernel, which is big and has a huge variety of authors, and it's this enormous thing. And so they use this compiler flag which says just don't do that to avoid surprise security vulnerabilities. MySQL, for example, compiles with a GCC flag called -f wrapv. This takes signed integers in C and C++ and makes them two's complement. Makes them two's complement for real instead of two's complement, instead of having undefined overflow. And why don't they want to go and fix those? I'm not sure. They're either I talked with them a while ago and I never quite got necessarily a strong sense of what it was, but either they're unwilling to go and fix them or they're worried about not being able to fix them all. Does that kind of make sense? So this is so -f wrapv is a mitigation for undefined integer overflow. A number of programs compile with the no strict aliasing. The Microsoft compiler, the Visual C compiler, doesn't support strict aliasing-based compiler optimizations. GCC and Clang do, but a number of open source projects turn them off in their makefiles because they're just worried about getting burned, or they know they're going to be burned by strict aliasing bugs in the code in question. And like I was mentioning, this is something that we hope can change soon if the LLVM-based type-based alias analysis sanitizer comes out and works well. So something that I'm really excited about that I think is super, super cool is some of Android, some limited parts of Android use some of UBSAN in the production release. So in the phone that's in your pocket, they are using, there are traps in that code for integer overflow. And not only for shift overflow and signed integer overflow, but in some of these codes for unsigned integer overflow. And so that's really, really cool. I think it's really nice that they've gone ahead and pushed that into production. And so there's sort of this general question of when can a detector also be used as a mitigation mechanism. And it's not just a question of overhead, right? So of course, if the detection method is like Valgrind and has like a 20-time slowdown, then obviously that's not a good mitigation mechanism. But it's also the case that the runtime for something like Valgrind or ASAN or whatever may add attack surface itself. And so it's not just a question of efficiency, it's also a question of have you added any attack surface. And there are some alternate runtimes for UBSAN that don't give as good error messages as the default one, but that are designed to be quite minimal in terms of code size and that shouldn't expose, at least hopefully expose any additional attack surface. And that's the kind of thing you can turn on. So this is very cool. And this is the kind of thing that I would, encourage people to explore is, can you turn these things on in production? If you can, it's very nice because then you don't have to worry about that one person finding the packet that triggers this particular behavior in your code. So Chrome on Linux is built with control flow integrity. So there's a very low overhead control flow integrity that avoids control flow hijacks. That's part of LLVM that's good enough to run as part of Chrome. This is super, super cool. And I think this is, these kind of things are, in some sense, less satisfying than the debugging because, we're sort of admitting that we haven't necessarily gotten rid of all the bugs, but in another sense, they're much cooler, right? Because what this means is that the last few bugs that we haven't been able to find aren't going to burn the product and cause major vulnerability. And so, like I say, I think the dissatisfying thing is these mechanisms aren't very standardized or portable. Like, what does -f trap v and GCC mean, and is it reliable? And these things don't necessarily receive a lot of attention or scrutiny, and it's not necessarily the case that they do the same thing across all compiler versions. So some of the mitigation space is, like I say, not particularly satisfying. Some undefined behaviors, like for example, race conditions, it's hard to think of a good way to mitigate these, right? It's hard to think of a way to mitigate concurrency errors. Memory safety error mitigation tends to be expensive, and so address sanitizer is not really designed as a mitigation tool. You agree? Good. It's not designed as a mitigation tool, and so one way to see that is it's often the case that address sanitizer, if you're an attacker, you just have to compute a different offset often. Does that kind of make sense? Okay. Kostya.
So if you don't mind, I will hijack your talk for a couple of minutes, maybe less. ASAN is not a mitigation tool, and I'm not aware of any technique in software that can mitigate memory safety bugs. But I'm aware of a released hardware-assisted memory safety mitigation, which is extremely useful. Unfortunately, it's only implemented in one CPU that probably nobody here is using. It's Spark M7. It has a very, very simple and very, very useful mitigation against this stuff. It's called ADI, Application Data Integrity, or something like this. And I want John's support and everyone's support here to push on the hardware vendors other than Oracle to produce something like this.
So ADI is very cool. But so Kostya, why don't you stay up there? So why not bounds checking? What's wrong with real bounds checking? So just so everybody knows, so ASAN fundamentally, uses this red zone based approach that could be jumped over. Actual bounds checking can't be jumped over. So is that not what we want?
Memory safety is two things. It's spatial and temporal. Spatial is bound checking and temporal is use of the free. We can solve bounds checking if we follow something like C++ core guidelines where the bound is attached to the buffer. We cannot solve bounds checking for the old legacy C++ code. But even the core guidelines looks like they're not helping against temporal, against use of the free. At least I filed a bug yesterday and with an example with string piece, a string view, where string view takes a pointer to a dead string and you have a use of the free. And even the core guidelines seems to not be helping. And we have legacy code from decades. And so we need to solve both at the same time. And the only thing that really, which is the closest to solving this is Spark ADI. It's not ideal, but it's so much better than anything we have.
Good. Okay, so production grade memory safety remains an elusive goal, and it'll be great when this finally appears, if it does. So, yeah, so like I was mentioning, so things like UBSAN can be configured as a hardening tool if you don't mind the fact that a bug might be turned into a denial service if somebody can trigger it. And that's just, I guess, a decision that has to be made on a project by project basis. Okay, so in my ideal world, what would happen is all of the 200 plus undefined behaviors in C++ would have one of these things done with it. So one thing we can do is a lot of undefined behaviors, and including a lot of the ones I didn't talk about because they're boring, could be defined. And this really, wouldn't be that hard to sort of say in the standard that that the implementation just does this specific thing. And I'm talking about all of the sort of fiddly undefined behaviors like the unterminated compilation unit or something. These kind of weird ones. Some of these weird limitations don't seem to me to need to be undefined behavior. That doesn't seem. I can't see the advantage of this. Another set of undefined behaviors can be reliably detected with fatal compiler errors. And this is, of course, a perfectly good option because then the software doesn't go out. And then as a fallback, the sort of last, the third place alternative, and this is sort of much worse than the first two, is to have a reliable runtime sanitizer. And so like I say, the reason that that's not as good is because then we need, then we don't notice the problems till runtime. And we're sort of not there yet, right? The situation has improved vastly over the last 10 years, and not all of these sanitizers exist, and so we're sort of getting to this place, I think, but kind of slowly and in pieces. So how are we doing overall? So not too bad. Overall, things are fine. Remaining big problems include production grade, bounds checking, strict aliasing stuff, and I think the situation might be improving there. Yes, Kostya?
If you don't mind, also you have uninitialized variables. And it's probably the simplest thing to mitigate, just initialize all the variables and all the heap.
Yeah, that would be pretty easy. And then we have minor issues like, for example, non-terminating loops and unsequenced side effects. That's an undefined behavior that I didn't talk about. Probably not a big deal, but it would be, these are just sort of easy things to fix that haven't been fixed.
When you say we should do one of those three things for every undefined behavior in C++, does that include undefined behavior in the library?
Yeah, because
so like every precondition on a library function should either not be preconditioned anymore, or should be diagnosed to compile time, or should have a sanitizer for catching violations of it.
Some of them will be slow.
That's a bold position.
But that's what Fortify tries to do.
Yeah, some of them will be slow, right? But that's fine. That's fine. Don't turn it on very often, right? Or turn it on for small inputs.
It's not the speed I'm concerned about.
No, it's writing them.
Yeah.
Yeah. Well, sure, that's right. That's right.
More than 200.
Yeah, that's right.
More like 3,000.
Yeah. Okay, well, I'm a professor, right? I can say things like this. So, like I say, so what I do is kind of finish up with my recommendation. So everybody who writes these languages has to be pretty familiar with undefined behavior, right? It's hard stuff, and we all need to know the big ones. We need to explicitly consider undefined behavior during code reviews. We need to test like crazy, right? It's like fuzzers are one part of it, manually written test cases are another, and then watching code coverage is another. And we all like to be lazy with code coverage, right? It's really easy to be lazy about this. We really need to lean on the code coverage tools, because this is the only time you learn if the fuzzers are actually doing what you wanted them to do versus getting stuck on some sort of getting stuck in some parser and not actually getting anywhere meaningful in your code. You have to stare at the coverage. This is super important. We have to all use the sanitizers and easy static analysis tools, and then fix the bugs they find. And this is hard, right? It takes discipline. But once we fix the bugs and get into a place where the software works, then it's pretty easy. And then finally, moving forward, maybe not necessarily now, but moving forward, we need to be familiar with the hard tools, with the tools that do more formal verification kind of stuff. And I think the future is going to include more of that stuff, at least for safety critical codes and for security critical codes. All right, so thanks, and I'd be happy to take any more questions.
Not quite a question, but a comment. Earlier was a discussion whether pointer comparison between different array objects would be unspecified or undefined. There is a change in the text between 14 and 17, which made it more clear, but in both cases, I think it says unspecified. In 17, it's very clear it's unspecified.
Thanks.
But
I was prepared for that.
So, do you feel that the committee should actually change signed overflow should define that behavior, or would you rather it stay undefined, or would you rather it go to it has a value but might not know what it is?
No, that's fine. I mean, I think the sanitizers are a reasonable answer there, and there's quantifiable benefit for the undefined behavior there. Something like shift farther than bit width. There doesn't seem to me to be any reason to leave that. There doesn't seem to be much benefit to that being undefined. But something like signed integer overflow is pretty. The fact that you can make some kinds of code faster by exploiting those facts, is pretty ingrained in how compilers work now, and I don't think it's really practical to back that kind of a thing out. That's not something I would argue for.
So you're not arguing to get rid of all undefined behavior,
No, not at all.
but to have realistic solutions to the problems.
Yeah, and, like I say, and the sanitizers are absolutely part of that, and and they're good enough in many cases.
Hello. I have a question about unsigned overflow detection. Is there any easy way to specify that I expect this operation to overflow?
Yes, the sanitizers have basically a little whitelisting functionality, and you can. And so the few of them where that's where you want that to happen, you can mark them, and then you get the automatic checking on all the rest.
Oh, it's an attribute. Okay.
Yeah. Otherwise, it wouldn't be workable, right? Okay, thanks a lot.